Welcome back. I'm recording now. Where we left off last week on Thursday is we were starting to talk about and finishing up the discussion of the different discrete buffers we have available to us in our rendering pipeline and what they are used for. And we briefly talked about different ways to deal with depth information and drawing these objects on top of each other. And in fact, one of the MP2 applications really showcases that, right? That rand triangles application, which is slightly evil, I guess. It's just drawing those triangles all on top of each other. It's very hard to know whether or not you have that working correctly or not, um, because you can't see all the triangles. They're on top of each other. You may be missing some, and you wouldn't even know it. There is that one approach that application is effectively doing that painter's method, which is I just sort things in the order I want them to appear. Draw the background things first, and then continue to layer and draw on top of things. There's no you know downside of that approach other than it does limit that sorting approach itself. It has some limitations, and if you want objects that are intersecting each other, self-intersecting objects, you can't do that with that just static sorting type of approach. So these image space approaches, or just if you just want to refer to as Z buffer based approaches, are much more common for that reason. We have dedicated hardware still today in modern GPUs to be able to support the Z buffer and the reordering operations that happen in the Z buffer. And this slide is showing what that means. That for our Z buffer, as we're rendering a scene, we are certainly clearing potentially our background color, our GL clear call. We had been thinking of as clearing just the pixel locations, the fragments we want to start as our drawing position. We want it to be a gray background, so we do GL clear color of gray, and we call GL clear of our GL color buffer, and it clears that back buffer for us. Simultaneously, when we do that, we also want to reset that Z buffer. Provide the initialization for those values, and it's going to be the same resolution. So for every XY location in our color buffer, we have the same number of locations in our depth buffer. So 1920 by 1080 different Z locations. For each of those locations, initialize at the same time we're initializing our color buffer to infinitely far, or whatever our maximum farthest away Z is going to correspond to in our scene. In our normalized device coordinates, by default, that would be 1.0, as far away as possible from us. Just like we specify our XY in those coordinates as being in that -1 to 1 range, we also do so for the Z information. So when it comes time to do our rasterization and we get our fragment back out, well, first off, it's important that we also do the interpolation um, of those coordinates. In our test so far, it's always been Z equals 0, so we haven't really seen the point of doing it. And boy, will that be an awful bug to overcome when you're on MP4. But at least in theory, in triangle setup, you're creating in the coordinates for all of those different attributes, including for the depth information, which for our inputs have been 0 so far. And you are interpolating those coordinates as you go. So if we have 3 vertices with 3 different Z values associated with them, all the interior fragments themselves will have an interpolated rasterized Z value associated with it. And then when it comes time to actually paint the screen, to update the color buffer, we first check, is this fragment we just generated and we're ready for render output, is it closer to the viewer of the screen, but is it less in the Z dimension than what's already currently there? For our very first fragment, and depending on how we want to do ties, but for our very first fragment, we should be okay. We've cleared the screen. We've initialized that depth buffer, the Z buffer, to as far away as possible. So anything we rasterize should be, at least in theory, closer than that. But for subsequent triangles and subsequent fragments we're generating, we have to check that. We know what our color should be. We have our RGB, and we'll talk about A in just a minute. We have our color information for our color buffer. Before we push that out and send it out to our color buffer, we have to do a read from Z, and determine, should we actually be rendering this fragment at all, or is it blocked? Is that particular fragment actually blocked by something that's in front of it from our view? And that's what allows you to do that order independent rendering, so that the order in which we specify our primitives, depending on the tie breaking rules, but by and large, the order in which we specify the primitives doesn't matter, because we're keeping track of how close they are to the screen, to what we're actually viewing as wanting to see as the two-dimensional representation on the screen. But our render output does become more complicated than what it is currently. Right now, it's take color, do a little bit of math on it, spit it out to the color buffer. We still do all those steps, but before we actually update anything in the color buffer, we have this read and potentially read, modify, write operation happening, which is read from the depth buffer, check that value to the current depth information that we have, and then determine whether we want to actually write to the color buffer. And we write to both buffers then, because we'd want to then update this XY location is this color, this shade of red, green, blue, and it also has this depth information updated associated with it. And that's the two writes that are happening here. So State Machine isn't really that much harder in render output to support this, but it does have to be updated to be aware of that. And that's what will give you your image-based depth buffer implementation. There's really no more to it than that. Um, to the point where actually, a demo of it is a relatively straightforward thing. But if we wanted this kind of scene, and this is just one of the very simple kind of default demos that I have here to show you, we can do so by just keeping track of the Z information for three-dimensional objects. So if we look at the actual wireframe associated with this scene, it's just a sphere and a conical solid here. And potentially, the dimension of those information of those objects could either be overlapping, intersecting with each other, or one could just be entirely in front of the other. If we don't have that depth information, the order in which we see these particular fragments here would depend on which order we specified them. But by supporting the Z buffer method, before we write any of these individual fragments, we're checking that depth information first. And that's all that this demo is showing. So when we think about our frame buffer, and this slide's actually from the very first day of the semester, there's multiple of these buffers potentially specified here. At the very least, we know that when we think of our color buffer, it's actually a couple different buffers, right? We want to, at least to avoid a little bit of the flickering that we've been seeing, we want to draw to the back buffer and display the frame buffer, and then swap those buffers to change which one's being displayed. So there's a couple 1920 by 1080 buffers associated with that. And there's quite a few other buffers as well. This one, we've just now defined that depth buffer. That's now storing in that same resolution what the Z information, the depth information is for each of those fragments. And depending on what we want to do for our rendering, there's quite a few other buffers that we can have here. One that I always like to talk about is kind of an old school way of doing it is the so-called sprite buffer. We don't see these anymore, but I think it's a good historical example. So this is in the very relatively early days of video gaming. We have a legitimate video game programmer here in the class. I don't know if he's on the Zoom call today, but this idea of you have in memory stored a series of the so-called sprites. So these little two-dimensional bitmapped images that you would then translate, scale, potentially rotate, and compose together to make a particular frame. This could be a separate topic if Steve ever wants to present this, right? So the idea is that you would have potentially a separate region of memory where each of these individual sprites would be stored. And they'd be stored in such a way to usually conserve our total memory usage. And you would have then a custom DMA engine whose job was to request two-dimensional blocks of region from that sprite buffer and compose them together with other two-dimensional blocks to create your scene. And here I am literally talking about our old school two-dimensional video game architectures and the software associated with them. And you would have hardware to accelerate that. At the very least, you would have hardware to basically do what we would refer to today as just a DMA operation, a two-dimensional memory copy operation. Give me this sprite, and if you're not old enough to know who any of these are, that's okay. It makes me sad, but that's okay. Take this two-dimensional sprite, or it makes me feel old. It doesn't make me feel sad, and copy it to a particular region on the screen. And in truth, this wouldn't have necessarily been an entire sprite, but this one certainly would have been an entire sprite. So copy that onto a screen, perhaps use an index color buffer to change the color of it or of how it gets shown on the screen, and overlay with what else is associated with that. So potential scaling, and then potentially selectively copied using a transparent color key. And the generic sprite architecture would look something like this. There's some semblance of a CPU, and depending on the architecture, of a modern looking CPU or a relatively what we would just call a basic microcontroller today, because the CPU is responsible really for just kicking off these series of operations. Some sort of either direct connection or shared buffer in which we would have our sprite buffer. And in the sprite buffer would actually be stored either index color or direct color information associated with them. So that's what the DMA engine would be doing. So we would specify that we want to grab the sprite, we want to scale it and make it 1/4 the sprite's original size. We would want to load it based on the location of the sprite in that particular memory, and then draw it at a particular location on that screen at that base address. So it's a little bit more than just a DMA engine like what we have in our SGP architecture now, because our DMA engine um, can do some of this, but certainly not all of this, right? We can do two-dimensional block transfers, or we can serialize it line by line, but we can't do things like scaling, or we can't apply blending operations directly in the DMA engine itself. But that was something that these type of architectures could generally assume, depending on what generation it was, more or less functionality associated with that. This actually goes back to what is supported in OpenGL. With those various buffers we have available to us, conceptually we can still consider all of our OpenGL memory as this kind of two-dimensional array of pixels and information associated with the pixels we want to display on our screen. OpenGL actually does have a whole entirely separate set of calls and a pipeline for reading and writing to just blocks of memory, basically DMA operations in OpenGL. We still use some of them, but now you can do so much with buffer objects that you can get away without having to use a lot of those operations if we don't want them. But calls like GL copy pixels used to be a very common one. If I wanted to copy a block of memory, that function call was very similar to like a DMA request, specifically in the GPU from this region to this region, copy these pixels, or from my CPU to my GPU, copy these pixels. And what we had in the early 2D system certainly is the special hardware, the bit block transfer, and the associated blitter hardware for merging that information. So if I want to be able to draw my little Space Invader on the screen, I have to be able to merge what's associated with the sprite with what's already on the screen, right? I have to take just the information that is to be drawn, in this case, just the on-off information, and not actually copy and overwrite what's currently on the screen for those parts of the little Space Invader that should not be drawn. Otherwise, it would just look like a big blob on the screen. You wouldn't be able to have different types of backgrounds associated with it. And there was at one point custom hardware to do those kind of merging operations and with different modes associated with it. If we want to think of this as just being 1-bit information for these sprites, but you could apply it to 8-bit and 32-bit color if you wanted to, you would have effectively a programmable lookup table in that particular block of hardware here, where we would take, as we're copying this sprite over, you would take that information, that 1-bit, the source pixel, and you would determine what to do with it based on a combination of what is currently in the buffer, in our frame buffer now, already there, and some function defined, of which if it's just a 1-bit value for both the source and the destination, that gives us a 2-input lookup table, right? Or a 2-input truth table here with 16 different functions defined, right? Because it takes a source, the 1-bit corresponding to that one location in the Space Invader is a 1 or a 0. Again, you could do this for 8-bit color, and very similar type of functions would be then defined um, with an all or nothing kind of mask applied. But for the 1-bit case, we have the 1-bit corresponding to that location in the Space Invader. We have what is currently in that location in memory already. Kind of like what we were talking about with ZBuffer, but a little bit different, because now we're actually looking at what's in the color buffer associated with that same exact XY location, and we're going to merge those two values together. That's the blitter hardware. That's the blitter operation here. And then with just different programmable modes, this one is showing just an arbitrary function. You can say this is an AND gate, but that's one possibility. And you would have, based on just the possibilities of 0 and 1 between source and destination, you would have the different operation modes. What would mode 3 do, for example? Any thoughts? By mode 3, I mean source comes in, destination is already there. Here is the output of this module to write to the updated pixel for our read, modify, write operation for each update to memory. What would function 3 do? So in general, this is all blending, no doubt. This is, and we'll talk about alpha blending. Looking at the truth table, and I don't know how well I introduced this, but we have what's currently stored. D is either a 0 or a 1. And what we're about to update is a new source pixel. It's also a 0 or 1. That's what this is showing here, right? So there's only 4 combinations of either a 0 1 is currently stored in the frame buffer, and we're about to update it with a 0 or a 1. And this is our programmable truth table. Think of it like a LUT in our FPGA if we want to. And we would literally have our LUT have one of these functions, or think of it like a CPRE 281 truth table where you do logic minimization and things like that. But your blitter hardware would be reprogrammed at any given time with one of these 16 functions. So I appreciate the attempt there. If we programmed it with function 3, which is this column of the potential type of truth tables that are possible, input S, input D, F function, or D primed is shown here. Give it a new source pixel, give it a new destination pixel. Here is our updated pixel. What would be the plain English explanation of what function 3 is doing? That's right. So you could have taken your 281 approach and done gate minimization. You can. It's totally valid. I mean, there's nothing wrong with it at all with that approach. But if we look at this function 3, it's equal to input S, right? So this would be an overwrite mode. This actually wouldn't be blending, for better or for worse, right? This would be overwrite whatever's in the buffer with whatever's in our source. Because when S is 0, output is 0. When S is 1, output is 1. D is a don't care if we were to do the logic minimization, right? It's a wire, a pass through. Just to finish this topic then, what would function 6 be? We're reaching way back into our 281 logic days. It would be an XOR. Yeah, that's right. Again, you could apply, you can draw a K map and all that if you want to. But I think for simple truth tables, we should be able to kind of just look at them and see what they're doing, right? When is this function 1? This function 6 is only 1 when S is different than D. When it's 0, 1, or 1, 0. That's our XOR condition. So that would be a type of merging scenario where we're using the sprite map to invert what's currently on the screen, which is a perfectly valid way of compositing something. 7 would be an OR gate, right? When S or D is 1, our output is 1. Some of these functions wouldn't be super useful. Like 0 would be clearing, 1 would be setting it all to on. And in ORs and XORs would be the most obvious modes for using this kind of hardware. In modern terms, though, we are doing something quite similar with blending things together, not necessarily for sprites, but for any of our objects we have in a given scene, with a little bit more flexibility in terms of what is possible. So if we were doing just single bit sprites and treating the sprite map as more of a stencil to be drawn onto our screen with that XOR gate, right, to either fill with color or not fill with color, a 1-bit transparency mask would have been sufficient. If I wanted to take this as my background and I wanted this object on top of it, you would use that hardware in 2 different modes. You would first AND the mask to zero out what the background area would have been, and then you just OR the result back in with the original image to get this composited on top of this. That is pretty old school blitter hardware. That's fine. We do conceptually a very similar thing still with regards to blending things together, where we have R, G, and B information associated with our fragments that we're generating. And we also keep track of now via an explicit alpha channel with how opaque we want that fragment to actually be. How much do we want to blend that fragment with what is currently in the frame buffer? So you can still use alpha information to do exactly this, where you have sort of a binary blending mode. And you can effectively implement all of these different truth table functions with our fragments as we go. Right now, we are doing by default mode 3, right? We're overriding whatever's in our color buffer with what we're generating now. But what we allow nowadays is providing explicitly an alpha information separate from the rest of our color information that lets us know how opaque or how translucent we want an object to be. So depends on which textbook you read what alpha equals 1.0 correspond to. But at one extreme, we have alpha equals 1, and that corresponds to a completely opaque surface. Overwrite what's on the screen. Mode 3 of that blitter hardware. And then at the other extreme, we have a completely transparent fragment, which may or may not be that useful, but there's reasons we may want to have that, which is allow everything to pass through. Don't overwrite any of the color information that's currently in the buffer. And then between those two extremes of 0 and 1, we have a sliding scale of how much transparency or translucency we have in that particular fragment that we're generating, in that range for those alpha values of 0 and 1. Depends how it's defined. You could define it exactly the opposite. But in this case, if we're completely opaque, alpha would be equal to 1. If we're completely transparent, alpha would be equal to 0. And in between those two extremes of alpha equals zero point 0.5, for example, that would be blend the information with what's currently there. That's what this picture is very briefly trying to show, which is this square drawn now on top of this one here is completely opaque. So the parts that are blocked via that Z information there, or just drawn after this background is drawn in our painter's sort method, you're only seeing the fragments for the second object that's drawn. Now, for this third object drawn for this triangle, there would then be some translucency associated with it. So instead of completely overriding what is currently here, what the value in the frame buffer for these particular overlapping fragments would be some mixing function of what's currently there with what we're trying to draw next. It's conceptually very similar to what the old school kind of bit masking hardware would allow us to do, but via that sort of sliding window of opacity allows you to do a lot more things than just simple gates of override it all or overwrite none of it and some XOR and some other modes here. This is partially overwrite. Overwrite via some fractional value that allows us to specify how much of the background we want to continue to be able to see through the foreground. And we could probably imagine why that's useful, right? Because in real scenes, you want to be able to partially see things. You don't want to just have a papered, layered effect for everything that we do. With very little additional hardware, this gives us a lot more realistic looking renderable scenes that we have here. So the model, this makes it look more complicated than it really is. But if we have now, again, our source and our destination colors or fragments, we have stored in our frame buffer something already at that location. In our color buffer, something in that location. You can think of the alpha channel as being its own separate buffer, but for a lot of color modes, including the 8-bit color mode we use this semester, it makes a lot of sense just to store it there with the rest of the color information. If we're using 8-bit RGB, our life is actually a little bit simpler if we also add the 8-bit alpha value there at the same time. Then we have these 32-bit fragments. A lot of our math gets a lot simpler for accessing memory. So we assume that something is already stored already, whether it's just the clear information or it's whatever was already rendered at that particular location, and we have a new fragment coming in. You've got your rasterizer working, you've rasterized, and you've interpolated that alpha channel now, right? We have to do that as well. And for that fragment, we have RGBA or RGB alpha information. We would then define somewhere in our OpenGL application and then stored in our driver and used in our hardware, the blending factors, which although I described here as being just kind of a single value alpha, we can actually specify that blending factor separately for each of the channels, including for the alpha channel itself. So we would actually specify both source and destination blending factors, of which there's simple OpenGL hooks to be able to do that. Usually the source and destination for practical purposes add up to 1. So this would be 0 and this would be 1, or this would be point 0.3 and this would be point 0.7, so that we don't wind up overflowing our color in common usage. And as long as it's a scaled percentage of each, you're less likely for that to happen. But we define those blending factors. How much of the source do I want to have? How much of the destination do I want to keep? And again, usually those would add up to one for the same reason as before. And then we actually calculate in our new pixel a blended value. Give me some percentage of the source plus some percentage of the destination. And just for red for now, that's going to specify how much of the red bleeds through, how much of the red of the background bleeds through. And we do so separately for the green, for the red. And what's maybe a little bit subtle is we also can then do it for the alpha as well, so that we wind up with a new fragment that has blended R, G, and B values, which that's the whole point. Also now blended alpha values itself. For then, if now the next fragment comes on top of that new destination fragment, we have to take that alpha value into account, and we continue to blend so that if you have 50% transparency on top of 50% transparency, the end result shouldn't be something that's 50% transparent. It should be maybe 25% transparent, because you can think of it like polarized lenses if you want, or just multiple layers of filters, but we're adding those blending factors multiplicatively on top of each other to get our final resulting blending factor here. Um, we are going to be storing it just like our color channels, just for simplicity's sake, if nothing else. We've been storing our color as these Q16.16, but I think those who really dived into the driver should realize, well, we really don't need that, right? If we're forcing them to be between 0 and 1, or we're assuming they're floats between 0 and 1, then a Q1.31 format would maybe make more sense for storing it, right? We don't need a lot of integer bits associated with it. And then likewise, I think you may have already seen back in MP1 that all that color storage kind of gets dropped anyway, right? Ultimately, we have a value between 0 and 255 for red, and for blue, green, and alpha with our 32-bit color buffer. So why have those additional fractional bits, right? I could have 1,000 fractional bits, but ultimately, if it's an integer color stored in memory that's an 8-bit int, all of those fractional information is going to be discarded. And if you look at a couple of places in how we do our triangle setup, there is some room for optimization if you can guarantee that this channel is for color information and ultimately will only have this much precision in it. Then you can actually start to truncate a little bit earlier and save a 4-bit carry look ahead adder and things like that. If you want to do that kind of micro optimization, we generally don't, but it's possible because ultimately we're dropping it. And I think we can do the same exact thing for the alpha. There's no reason to say for certain that an 8-bit alpha is sufficient for 8-bit color in the other channels, because it does kind of multiply. Eventually, you will underflow your alpha information, but I think it's okay. And a couple other questions were good there. So usually it depends. So we have these kind of orthogonal modes in our OpenGL application where we're specifying what our depth function is, and then we're separately specifying what our blending function is. Usually, for a given part of the scene, you're worrying about one or the other. That if you're doing alpha blending, you're going to be turning off your depth testing. You may still be storing all that depth information for later, because you may, for further purposes, after you've done all your alpha blending, want to know how far away this particular object is for the same reason we want to know before. But usually, if you're blending, you're not discarding fragments. You're blending those fragments, right? You're deciding, I always want both because I'm blending them together. I don't want to drop any of them. So you have somewhat orthogonal modes of rendering in your application, where you're specifying what I want my Z range to be and what I want to do. Do I want greater Z values or less Z values? How do I want to break ties? And then you have your alpha blending modes, of which we get to specify, what we want our blending factors to be for each of the color channels. And usually for a particular part of the render, it's one or the other. That if I'm blending, I'm not dropping due to Z test. You can see some very basic examples in our old school OpenGL code. Um, I don't know how I can see that. I'll make that a little bit larger here, where we're just drawing four quads on top of each other with the different blending modes possible. And you can just change the blending function here. I don't know how well that's going to show over our Zoom channel here. So I've turned blending off. So if I turn blending off, then the order in which I draw these matters quite a bit. And then for the different blending functions, of which I very briefly mentioned it on the slide here, uh, for certainly for your old school OpenGL, you can specify for those B and C values, whether it's 0 or 1, or whether it's 1 minus source alpha, taking the alpha information that's stored and using that to choose the new blending equation for those values. And that's all this application is doing, is just cycling through the different possibilities for the blending function there. So finally, we're basically done with this topic. But finally, when we're talking about things like rasterization of lines and triangles, and there was a couple of good discussion topics on that as we were digging into MP3. I think the problem is, as we're in this triage stage of trying to fix bugs and trying to get triangles to work, it's hard to have discussions also on like the higher order questions at the same time. So I think it's nice that these topics are kind of interleaving and we can come back to them as needed. This issue of aliasing. So any of you who've taken like a W224 style class, or even just have any interest in audio, may be aware of fundamental issues of sampling a signal and potentially having a high frequency signal kind of being hidden away as a low frequency signal. So if I have my high frequency sine wave here and I'm only sampling it at a certain rate, and that sampling is not at the Nyquist rate and all that, but it's not fast enough, we'll just say. I'm grabbing a real analog signal and I'm not sampling it fast enough, you may wind up with a sample that's extremely, if nothing else, misleading, or at least has serious aliasing here. It's not capturing the actual higher order information of this signal here. Um, in general, it's a signal that you can't perfectly reconstruct because you haven't been grabbing the information fast enough. So we have issues of aliasing for all sorts of reasons. Having insufficient precision in your arithmetic is going to lead to some types of aliasing, right? As we are doing our rasterization algorithm, we are making precision assumptions by having that fixed point format, and that's going to lead to aliasing. But in general, when we're rendering anything with any rendering approach, with any algorithm, with any precision of implementation, there's a fundamental challenge of aliasing because our sample is ultimately the screen that we're displaying something on. I don't want to get too much in the weeds of that, right? But our pixel is ultimately a sample of some signal in that two-dimensional space. And for a 1920 by 1080 resolution screen, we have that roughly 2 million samples that we're doing of our signal. And if we had wanted to display something that is the two-dimensional analogous case of this signal, of this signal, this high frequency signal, and our pixels are this far apart, we're going to fundamentally have that issue of aliasing, where we can't reconstruct an image that has that much more transitions happening, that much more change in features happening than what can be displayed on that much resolution. So no matter what, it's not just an arithmetic issue. It's not a sloppiness issue necessarily either. It's we're fundamentally having an issue with aliasing where we're drawing a line. And we saw this already, but I think those of you who've been really zooming in on our triangles, one team had the floating pixels, but I think that was a bug and not an aliasing issue. But as we're zooming in on our triangles, our edges for really sharp triangles should look pretty bad, just like they would be for our lines. That's fundamentally, at least for our existing implementation, an issue of aliasing. We're trying to draw a very high frequency thing. The high frequency thing we're trying to draw is our gradient in the x and the y dimension. And we're trying to draw it using an approach, at least, that's taking these 1 pixel hops at a time. It's a fundamental limitation, always, of our screen resolution, But in this case, it's also a limitation of our rasterization approach. Our delta x and delta y is 1.0 pixel for that implementation. We are either turning a pixel on or turning a pixel off. We are either in the triangle or outside the triangle. We're making determinations at that frequency. 1 over 1920 in one dimension, 1 over 1080 in the other dimension is effectively our sampling rate, our way of making decisions at least. That's effectively our rate. And if we are trying to render things that are having change at a more frequent rate than that, we're going to have to make decisions that will effectively look like this, where we're going to get a low frequency version of that implementation. There are solutions. I regret to inform you that at least for our in-class labs, there are no solutions that we will be doing, but there are solutions that work for this. It's potentially a project idea to try to fix this issue. But just to visualize it here before I go into that, for our lines or edges of triangles, that aliasing effect is that jagged information, right? Where we're making these decisions of plus 1 pixel in one dimension or the other. But our line actually has information that is more subtle than that. And so when we actually look at that line that gets rendered, if it's at that resolution, it doesn't look very good. But we know what we would actually want to see would be something that would have sort of a smoother gradient to it than that. That wouldn't either be white or black in this case, would maybe be some shade of gray to allow us to make it look a little bit better. Lots of different solutions for it. Looking at a region of area around the particular decision and determining the percentage of overlap is one such approach. So if we're just rasterizing lines, one way to do that would be to instead rasterize a 1 pixel wide triangle and to take the percentage of overlap as not just a binary choice, but that percentage giving us a color information. That instead of white for not covered, or in this case black for covered, it would be a percentage covered, and that would be our grayscale information associated with it. So based on that, we can then determine, it's very easy to visualize, but much harder to implement in practice. We could then determine, what percentage of an individual pixel should be covered by that particular line. Doesn't look all that much better. In fact, it looks a little blurry, but that's because it's kind of blown up here. But in general, this would lead to less jagged looking edges of our primitives in a design. The other issue teams have seen is when you have, for our triangle strip, you have adjacent triangles. Our approach should be okay in terms of having holes in our adjacent triangles. If you're seeing holes, I still think something is not quite right with your implementation, because we're always making that rounding decision consistently. Just like with Breshenham's approach, right? We're basically still doing that in our rasterizer. As you have two adjacent triangles, whether the left triangle is on that pixel or the right triangle is on that pixel should at least be a decision that's being made consistently from one triangle to the next as we do that implementation. But still, it's going to be a jagged thing for that same reason. We're doing +1 in that resolution decisions for our plus delta x plus delta y. We're setting that to be 1 pixel. And so we're going to see, closer to that kind of edges of our triangles as we're rasterizing them. There are approaches. A much more, I would say, common approach today, and there's a lot of art to this. I think a little bit more than science, but this idea of just super sampling your image. So, or appropriately sampling your two-dimensional space here. That even if your final resolution display is going to be 1920 by 1080, as you're actually doing the rasterization for those fragments, and modern GPUs look at them as clusters of fragments at a time anyway, you instead consider that pixel, that individual 1 over 1920 and 1 over 1080 region in our sampling space, as actually being composed of multiple subpixels. Either a 2 by 2 grid or 3 by 3 grid, some sort of square grid of micropixels. Where if this is our center pixel in our actual display that we're interested in determining what color it should be for that given edge of a triangle or that given line that we have here, as we're doing our actual rasterization, and only potentially for that part, we wouldn't have the space to be able to have a super sampled frame buffer necessarily. But as we're doing this actual rasterization, we're instead thinking of it as being, in this case, effectively a 4x resolution target for us. So our delta x and delta y would be 1/4 of that. We would divide our individual pixel into subpixels, and we would then determine the color of our individual subpixels, and then with some sort of post pass, do some sort of averaging of what the subpixel coverage would be. In this case, I think we see it, right? We would like this to be not white, not black, but maybe 60% covered. Well, if we only have 2x by 2 by 2 super sampling here, we could determine that perhaps Breshenham gives us that two of these are being covered, and so we should color this at 50%. That's going to give you a smoother looking gradient of our edges of our lines and our triangles here. So in modern systems, there's all sorts of different approaches for anti-aliasing with different sampling patterns. It's not as simple as now as you have these larger grids. What researchers have shown is that you can have actually quite large grid. You can have 8 by 8 and even 12 by 12 size micro grids, but you don't have necessarily the processing power to do a 12 by 12 pass through that entire grid. Instead, there's a particular traversal pattern you take through that grid, and then you can still effectively average the results or treat it as a filter over that particular pixel that you're looking to generate the result for, and it gets really good results. But it's still effectively the same idea of super sampling, where in hardware, as you are processing this pixel, consider in fact that you had a 4x the resolution or 9x. It grows, quadratic, right? Or 16x or 25x the resolution of what you actually are rendering to. Only for the purposes of rasterization, your end result is still going to be a fragment with a set of attributes associated with that pixel location in our frame buffer. But as you're doing the rasterization, you can assume a much finer tile, and then you can do some averaging and other filtering approaches to get a result that makes sense at the end. These are kind of fun. If you want to look up what modern hardware does for MSAA and other things, um, there's a clear path between sort of doubly 224 filter theory applied in a discrete sense to getting anti-aliased results in your modern video games. It's a bit of a stretch. 224 certainly doesn't cover that. Even some of our image processing advanced 400 level classes don't exactly cover that, but it's clearly based on that type of application of that exact theory. My anti-aliasing demo is not going to look very good because I don't think you're going to be able to see the difference in this screen here. Um, Here's our aliased view. It's going to be pretty subtle, but if you can see the edges of that, this is actually supposed to be a sphere. It's the same benchmark data as before. The edges of the sphere should look pretty mediocre. And again, that sphere is just composed of triangles. And because of the edges of those triangles, you can really see where it looks like a low poly sphere, and it's really actually not. And then if we turn on the aliasing, we get a somewhat smoother blending of the edges around it for that particular sphere. In your zoom window, those two examples may have looked identical, but they were not supposed to. I want to jump topics because as we jump into uh, MP3, you know, supposed to be today. But as we jump into MP3, I guess on Thursday, we're going to be doing an applied version of viewing transformations. We've already been doing a little bit of viewing transformations. In MP1, you built a viewport module. We didn't really talk about the why. I just said implement this, and you implemented this, and it worked just fine. Today we're going to be, and starting today, and then continuing on into next Tuesday, next Thursday, we're going to talk a little bit about the math behind how we do viewing and transformation. So, if previously we were covering for rasterization, fourth grade math, we're all the way up to seventh grade math now for the math required for doing viewing and transformations, and then seeing how that applies to that math, how it applies to actually viewing a three-dimensional scene. And that's what's finally going to allow us, with also the depth buffer and the discrete space there, going to allow us to view three-dimensional things on our graphics hardware that we're building. Depth buffers not necessarily sufficient. It'll allow us to do manually drawn three-dimensional things. These transformations that we're going to apply to them via programmable processor for MP3 is what's going to allow us to really have dynamic three-dimensional scenes. So there's a little bit of math. We'll dive into it a little bit today, and then we'll definitely be able to pick it up and cover it entirely properly. And having said that, while this topic is entirely about three-dimensional math, I personally, this is my own bias, find it a lot easier to view it with two-dimensional math first, and then just do a direct extension of that uh, two-dimensional math to then adding that z dimension to it. So, but the whole point of this stage, whether geometry is really the right word for it in modern GPUs, our vertex processing stage. The whole point is to figure out that when I specify a position in my XYZ space, my vertex buffer, determine where that corresponds to in my window. Now, you may be saying, hold up, we already are doing that, right? We have a viewport module, that's this fixed function module that does that. That viewport module is doing the very final part of that, which is given an XY, in this case only XY, in the range -1 to 1, it figures out what fragment location on the screen that corresponds to. That's all that viewport is doing. In the more general case, for an arbitrary XY location in any range, or whatever range we could support in our fixed point hardware, determine where that should correspond to as then an input to the viewport module. So it's a fundamental challenge that will allow us to apply a couple of techniques, and we're going to start with the math for the 2D case. It's just easier to view what's happening in the two-dimensional case. So this is the part of the pipeline we're starting to understand now. You have a decent, I think, handle on what's happening here. We know a lot of what's happening in our buffers. You haven't implemented any of the blending or Z stuff yet. It's very doable, and you'll be able to do it in MP4 without much direct instruction in code. And I'm going to tell you to do it, and you should be able to sort it out. We've almost finished this. We're really close. And then MP3, we're going to be implementing this, which is another better term for it would be the vertex stage, vertex transformation stage. Given input vertices, transform them so that they're ready for the rest of the pipeline. In a sense, it's working backwards, right? But we've been okay because we've been forcing our OpenGL applications to be really constrained in terms of how they specify their vertices, and then the rest of the pipeline just works for us. We're going to be able to break that limitation and allow us to do things like rotate objects in three-dimensional space, and all that processing is happening here. And if this stage does its job correctly, we get an output that is in that -1 to 1 range on the output side of this, as opposed to also on the input side, and the rest of your hardware works as expected. That's the goal. That's the idea. So in a sense, we're working backwards. Well, these labs aren't a lot of fun if you don't have a display, and they're really painful if you can't work with triangles. And now we're going to finally be able to work with some three-dimensional triangles here and manipulate them in various ways. Having said all that, we'll start with two-dimensional case, at least briefly here, and we'll be able to add that additional dimension here. Truth be told, I don't entirely know for a computer engineering student, and I have a better feel for electrical engineering student, how much math background you have. This is not hard math, but if you're finding some of the vector math a little confusing, I can provide you a lot of resources. I can walk through it with you in office hours. From the computer engineer's perspective, I would say the math is a solved problem for doing vertex transformations, and it's more of an API and understanding how to use those type of problem. But we'll cover the math first, and then we'll talk about the APIs as well. So our goal is to be able to manipulate our vertices, and consequently the triangles that we are generating as part of those primitive objects we have here. And there's various other transformations we would want to be able to do. So we'd want to be able to move it. I want to move my triangle from left to right. Right now, for MP2, if you want to move your triangle from left to right on your screen, like in that Try Paint app, another team came up with a really cool demo application. What would you do? You would have to, right now, for MP2 hardware, you'd have to calculate new vertices, GL draw arrays, copy those new vertices over, and re-DMA those vertices through our pipeline, because we can only move things in software. But in general, we want to be able to move things pretty effectively. We want to be able to translate our triangles around, our objects around. We want to be able to rotate them. We want to be able to make them larger or smaller. And there's other things as well. We want to be able to reflect them on the horizontal and vertical dimension. We want to be able to squish them and shear them and do things like that. And we want to be able to apply fairly general transformations to our objects. The nice thing about triangles, at least for our vertex processing, is that as we translate the vertices that compose our triangle, we get an effect on the entire triangle without breaking the fact generally that it's a triangle. So while for on a vertex or a point by point basis in our two-dimensional space, our goal is we want to apply some function to it. So for our input point, we want to apply some function in the x and y dimension and get new values x prime and y prime here. And we can start to visualize that as xy in our vector form. There's all sorts of things that in theory we could do. The world of nonlinear transformations is infinite, right? In terms of what we want to do. We could do all sorts of things for which, as we translate our points that comprise our triangles or other basic geometric shapes here, we wind up with things that are very much no longer triangles, potentially. Um, Anything we want to do in the nonlinear stage. So we would then take, if that's the case, if we wanted to apply that transformation, we would need to apply that transformation not just to the points of the triangle, but for every point inside our rasterized triangle. And that's a much more complicated thing to do. The nice thing about it is, while in theory we want to be able to apply those nonlinear transformations, in practice there's a lot we can do with composed linear transformations. So this is a lot harder to deal with. Our rasterizer itself would have to be able to apply these transformations, or there would have to be some really custom per fragment transformations happening here. We eventually will have that capability, but with linear per vertex transformations, there's still a lot we could do. In theory, we may want to apply this arbitrary nonlinear function. This is a completely arbitrary one. What would that do if we applied that to every pixel in our XY space here? I mean, I just draw something kind of silly, right? So I don't know what it actually would correspond to. It would deform it somewhat severe as we're applying something nonlinear. In general, though, what we want to do is to apply a linear transformation. So in the general case, we're going to want to take a point xy and apply some potential scaling to it and potentially some transformation to it. The advantage of this formulation, where it's linear, is that as we transform vertice xy to vertex xy to vertex xy prime, and we have a line in our original specification, it's still going to be a line. So if we have a triangle and we transform all 3 points in the triangle the same way, and we apply the same transformation to all 3 points, our end result is also going to be a triangle. That's a pretty big advantage. Whereas to actually calculate the abstract house here, we would have to apply it to each fragment. So we can do relatively computationally efficient per vertex shading here to transform our input vertices in a linear fashion to be something else. Such that given an input xy, we would then have as some specification AB in the x and y dimension plus some C translation factor, or just think of it as some matrix we have to calculate and determine plus some translation factor. And as we'll see here, and this point's going to be important, so I'm going to want us to cover it properly, our hardware for our math gets even simpler if we can refactor this expression such that we get rid of the translation itself, and we'll be able to do it. So let's talk about some of the transformations that we are capable of doing with basic linear algebra here. Translation is one such transformation. We want to move something, in this case in our 2 dimensions, in our xy dimension, where we would apply for every input x in our triangle or in our shape, some translation in the x dimension and some translation in the y dimension, or more carefully, our new point is our old point plus t, where t is a two-dimensional vertex here. Our inverse transform is just subtracting that same translation array here. So for our specified points in our vertex buffer, if we were then to apply this transformation, a translation, of 4 in the x and 3 in the y, we would get this kind of resulting triangle shown here. And hopefully you can start to see the savings, the whole purpose of why we have vertex shading in the first place, right? To do this geometric transformation. You could also do this in software. And that try paint application does that in software, right? I want to move where my triangle is and move where this vertex is and I do so by just recalculating all the vertices and restoring them. But if I want to move this entire triangle, assuming I have hardware to support doing this type of operation for me, all I have to update is this information here. So for one triangle, that doesn't seem like a huge savings, but for a million triangles, that's a pretty significant savings, right? I want to translate every triangle in my scene by a certain amount. All I have to change in this case, if we assume we have hardware that can do this math for us, which we will, in fact, your MP0 hardware is doing exactly that, right? Um, or some flavor of that. All we have to update is the matrix, or the transformation matrix associated with it. So this is one translation. Shift things around. Uh, Visualizing that in Z is just a little awkward to do on a slide here, but you could also think of that in your third dimension as well. TX, TY, potentially TZ as well. So there's our translation example. We don't have to actually do that. I think you guys can do paint and move vertices around. Scaling is a bit more subtle, but follows a very similar principle where we want to transform our x and y by some multiplicative factor here, sx and sy. So now it'd be more of a matrix vector operation happening here. Definitely what our MP0 was looking right? So that if we want to scale it in the x and y, we would then encode a matrix such that when we multiply this 2 by 2 by our input point p, our xy, we get sx times x plus 0 times times y plus 0 times x plus sy times y, and we get our scaled point back out. Technically, it's scaling relative to the origin for that reason, but that's something we can work with at least. So if we were to have this scaling matrix of a factor of 2, for every point in our triangle, we'd be basically just multiplying and getting 2x and 2y back out. So this lower left-hand point is 1, 1, it becomes 2, 2. This one is 3, 1, it becomes 6, 2. We wind up getting a larger triangle for that reason. And in this example, the x factor scale and the y factor scale are the same, but they don't have to be. They could be something arbitrary. We can also get our inverse transformation back. Just like in the translation case, we just subtract that same matrix. In this case, it's the inverse of the scaling factor. I have to be a little careful with the terminology here. S inverse is not the inverse of this matrix. Well, actually, it is. So it's fine. So it's the inverse of that matrix, which is the inverse of the scaling factors here. So if we want to get back to where we were, we just have to do the inverse of sx and sy to get our initial points back. So it's translated relative to the origin. So it does kind of look like it's a little bit of a translation as well, right? Not only is that triangle getting a little bit larger, it's also being moved a little bit in the upper right direction because of that scaling. As we can see, we can definitely compose these transformations so that we are scaling relative to its object center and not the origin of our coordinate. So that's just a side effect of doing math relative to an origin. That is, we multiply x and y by a factor, we're getting further away from the origin of our coordinate system here. Um, Scale lets us do all sorts of things, right? So you may have already been thinking about it. We can certainly do a uniform scale. That doesn't preserve the length, but if we have a right triangle with those angles, we will get the same angles back out when we do that scale. We can do non-uniform scaling, right? We don't have to have Sx and Sy be the same. So this is what's going to allow us to shrink and stretch our triangles in various ways. We can do reflections around axes for that reason, right? By just setting one of the values to be negative for the Sx and Sy, and we can then do a reflection across both axes as well, right? So we saw this in MP0, and people were asking. I said, well, yeah, this is fundamental to doing computer graphics. We'll talk more about this, and certainly in our next lecture on Tuesday, we'll talk more about this. But this is the reason that matrix vector math is fundamental. We're going to be wanting to be specifying our vertices once for a given scene or for a given object. Specify the vertices once, and then manipulate what that object becomes by applying these transformations over and over and over again to those vertices as they come through. So that hardware we built in MP0, while a bit of an extreme case, what we were trying to do for that MP0 example, is very similar to what our vertex shading hardware needs to be able to support, at a minimum, which is taking an arbitrary matrix, and applying it to the input vectors as they come in, which is our points in our XYZ dimension here. So while you probably won't be reusing any of the code for MP0, the same math is going to be applied as we are doing our MP3 math, just via a slightly different mechanism for that. Let's leave things here for today. I want to make sure we cover this properly so that the whole point of MP3 makes sense and it doesn't seem like magic code that you're running for MP3. But we will do that a week from today with our demo day on Thursday. And I'm excited to see the success. And if they're failures, that's fine. Just at least make them spectacular failures for Thursday. Otherwise, let's leave things here for today. Let me know how progress goes. Otherwise, I'll see people tomorrow in lab.